So in this video, we're gonna start a new chapter, and this chapter is about functions, which is gonna be a very, very important topic because the ideas that we will discuss in this chapter have been coming up and are gonna come up again in almost everything that we discuss. So what is a function? A function is like a computer. So you have a function f. It takes in an input. Let's say that your input is x, and it provides an output. And we call this output f of x. So let me illustrate. If I write a function f of x is equal to x plus 1, right? This f is the function. My x is the input. X plus 1 is my output. So f of 1, I input 1. The output is 1 plus 1, which is 2. And so on. So a function basically works like this computer. It takes in an input and it gives you an output. And a function must satisfy this thing. Every input is mapped to one specific output. So basically, every input is mapped uniquely to one output. And let me just illustrate. So if I have something like y squared is equal to x, right? If I have this equation, then suppose x is equal to 1, right? So y squared is equal to 1. Y can be plus 1 or y can be minus 1. So my input, which is x, is being mapped to y is 1, and it's also being mapped to y is negative 1, right? So my input is not being mapped to a specific output, it's being mapped to multiple outputs. So this is not a function. This is actually a relation. A function is a very special type of relation. So this is what we call a relation. A relation is basically a mapping. A function is a special type of relation where every input is mapped uniquely to a specific output. So you can't have one input being mapped to many outputs. That is not a function. And that is one way to check whether something qualifies to be a function or not. So we have something called the vertical line test. And the vertical line test comes from this idea, is that if you know the graph of your function, if I know the graph of my function, then I know, so if I know the graph, then I know whether or not it's a function using the vertical line test. So this test will tell us whether it's a function or not. So suppose I have my coordinate axes like this, and I have a curve like, say, like this, right? So now I want to draw a vertical line. How many points does it cut? Only one. And just keep doing this at every point, right? So wherever I draw a vertical line, it's only gonna cut the curve at one point, right? My input, which will be on my x-axis, only corresponds to one output. But suppose I have something like a circle. So I draw my coordinate axes again. So that is a function, right? If I draw a vertical line everywhere and it only intersects the curve once, that is a function. But suppose I have this, and I have something like a circle, like this. All right, so if I have a circle, I draw a vertical line. At any point, it's gonna intersect the curve at two different points, right? So for 1x here, I have one value of y up, one value of y down. So one input is being mapped to two different outputs. It's not being mapped uniquely. It's not being mapped to a unique output. So this is not a function. This is a relation. So a function is a very special type of relation where one input is mapped uniquely to a specific output, right? So when we talk about functions now, and we've discussed functions as mapping, so f of x is equal to x plus 1, right? So we're mapping x's. So we're taking, this function takes values from this x set of x values, and it maps it to this set, which contains x plus 1. So if I have 1, then it's being mapped to 2, right? If I put 1 here, it's being mapped to 2. If I have 2, it's being mapped to 3. If I have 3, it's being mapped to 4, and so on. So we have something called a one-to-one mapping. So a one-to-one mapping, or a one-to-one function, a one-to-one function is basically when no two inputs map to the same output. So basically, the mathematical way of representing this is that if x does not equal to y, then, so this is saying if x does not equal to y, then f of x does not equal to f of y. Or another way to write the same thing is f of y is equal to f of x is equal to f of y, then x is equal to y. So this is the test that we will be using to check whether a function is one-to-one. And if it's not one-to-one, then it has to be many-to-one. And a many-to-one function basically is as follows. So a many-to-one basically means that you can have two different inputs can map to the same output. And let's use the example f of x is equal to x squared. If I put f is equal to 1, if my input is 1, my output is 1. If my input is negative 1, the output is still positive 1. So two different inputs can map to the same output. Many can map to 1. So that is a many-to-one function. And one-to-one means every input maps very uniquely to one output, and basically if the outputs are equal, then the input has to be equal, right? Or if the inputs are different, then the outputs are different for a one-to-one mapping or a one-to-one function. So what you cannot have is one-to-many. This is not a function. This fails the vertical line test if you draw the curve. This is a relation. This is not a function. And let's use the example, y squared is equal to x, right? X is equal to 1 corresponds to y is equal to 1 and y is equal to negative 1, right? If you put x1 here, y plus or minus 1 both satisfies this equation, this relation. So you have one input corresponding to two different outputs. You have one corresponding to many, that is not a function. And if you draw the curve of this equation, it looks something like this. Y is equal to x squared. It's a parabola, but it's, instead of the usual, we draw it on our x with respect to the x-axis, right? If you do the vertical line test, it intersects twice. So it cannot be a function, right? You draw a vertical line, you see that it usually intersects the curve at two different points. That means one input is being mapped to two different outputs. That's the relation. That is not a function. All right. So now that we have discussed the important part, let's discuss two words that we're going to be using a lot in this chapter. And the two words are called domain and range. So domain is the set of permissible values, permissible input values for a function. Okay, I thought my microphone was off for a minute. Okay, this set of permissible input values for a function is the domain, and the set of output values that the function can map to is the range. So basically, domain is a set of permissible input values. What values of x can you put into a function? That is your domain. And what is the range? Is basically what are the output values that the function is mapping to. That is going to be your range. All right. So basically, the set of output values is called the range. The set of acceptable, permissible input values for a function is your domain. So now let's look at common, very, very common functions that we will encounter. And we'll look at their domain and range. And we'll look at their graphs as well, because knowing the graphs is very, very important. So the first function is your linear function. And your linear function is expressed as f of x is equal to mx plus b, right? M is your slope. B is your y-intercept. And basically, you can try drawing the graph. Because we don't know m and b, I've just kept it as very random. So let's just say it looks something like this, right? This is b, and the gradient is your m. So let's just say it looks like this. The domain for this function is that x can be any real value. So any x is okay, any real number. So later we will discuss complex numbers where you have imaginary numbers, but anything that is not imaginary, right? Anything that does not contain I, which is the imaginary unit, all real numbers you can put into this function and you will get some output. So the domain is all real numbers. And this is how we express it. X, this means, is an element of real numbers. X is an element of, and this is the set of real numbers. Real numbers. All right. Now let's discuss the range of this function. F of x is also going to be all real values. So it's going to map to all numbers from negative infinity to positive infinity. So another way to write your domain is as follows. You can say x belongs to anywhere from negative infinity to positive infinity. And infinity, you can't exactly have infinity, so we're going to use open brackets. Open brackets means it's not exactly negative infinity, anything that is bigger than negative infinity, and anything that is smaller than positive infinity. Whenever x is within that range, that restriction, then your function will produce an output. And your range, what output values does my function map to? Well, it's the same thing. My f of x is also mapping to negative infinity to positive infinity. It maps to, if I say y is some mx plus b, or f of x is some mx plus b, f of x is also an element of real number. Basically, it maps to all real numbers. So your domain is from negative infinity to positive infinity for all linear functions, and your range is also from negative infinity to positive infinity. All right. So now let's look at our quadratic functions, right? And it depends on how you draw the curve as well, actually. But let's use our example of f of x is equal to x squared. Let's look at the graph of this. So the graph looks something like this, right? So your domain, what values of x can you put in? Well, you can put any values of x. So x is an element of real numbers, you can say that. Or x belongs to anywhere from negative infinity to positive infinity in an open interval. And what values does this map to? The range. What are the output values? Now, if you look at this, you can see that your output values are always bigger than or equal to 0, right? You don't have negative output values. You don't have anything here. The function never maps to anything negative. So your range, if f of x, is always bigger than or equal to 0. So the range of this function is that it maps to 0 or positive real numbers. So your range for f of x is equal to x squared is f of x is greater than or equal to 0. All right, or you can say y is greater than or equal to 0. That is also okay. All right. So another common function that we will encounter is the square root function. F of x is equal to square root of x. So when we discuss square root of x as a function, and again, this is because we haven't discussed complex numbers yet, so we don't have to introduce I. Your square root function looks something like this. It's growing, it's increasing at a decreasing rate, something that we will discuss later when we do calculus. So the domain of this function is, if you now think about it, you cannot put negative numbers inside the square root of function. F of -3, suppose -3, this is not defined. Because remember, when we said domain is the set of permissible values, accepted values, right? So domain is x has to be bigger than or equal to 0. X, this is my x-axis, has to be bigger than or equal to 0. And my range, again, if you take the square root of a positive some number, you're not going to get anything that is negative, right? So your range is going to be f of x is bigger than or equal to 0 as well. Basically, your output can be 0 and it goes to positive infinity. So another way to write this would be f of x is an element of, now I use a square bracket here. That means 0 is included, goes to positive infinity. So open bracket here. That means that positive infinity is not an exact value, right? It's just a concept. So we use an open bracket here. We use a closed bracket to indicate that it can be 0. All right. So square root of x, x squared, x cubed. Also a very important function. So the function f of x is equal to x cubed looks something like this. So it looks something like this. You have an inflection point at x is equal to 0. We'll discuss inflection points later as well. So your domain is just x is an element of real numbers. Your range is basically f of x is an element of negative infinity to positive infinity. It can be anything. Basically, f of x, your output values is all so real numbers, mapped to all real numbers. All right. Another common function is your exponential function, a to the power x. Right? So for a that is bigger than 0, so positive a bigger than 1 as well. Sorry. For a bigger than 1, it looks something like this. And we've discussed this, right? Looks something like this. So your domain, and actually if a is less than 1, it doesn't change. Because say if you have like 0.5 and you raise it to something very big. So the graph, if a is less than 1, then it just flips over the y-axis, so it looks something like this, but it doesn't matter. The domain and the range does not change. But the graph, how the graph looks like changes. So the domain is x can be all real numbers, right? You can put any negative x, you can put x as 0, you can put any positive x. But your range is strictly, it's never going to be 0. You raise a to anything, you're never going to get 0. It's what we call asymptotic. So it's not possible to be 0 and it's always bigger than 0. So your range as f of x is always bigger than 0. So you can try it with your calculator. You pick a, say let's a can be your Euler's number, a can be 10, a can be any constant value to the power x. And you try just substituting in numbers. You put any negative value as big as it, as small as it is, any positive value, and you will see that your output is never 0. It's always going to be bigger than 0. So that is why, because it's never 0, we're going to use an open bracket here. And infinity, you can't exactly have infinity. So your range is from open bracket 0 to infinity. Or you can write it as f of x is bigger than 0. And one more function would be your log function, right? So log base a of x. Or ln x, right? So for, again, this is for a bigger than 0. If it's a smaller than 0, then the graph flips over, as we've discussed. So something like this. So your domain, so let's just discuss the natural logarithm, ln x. That's easier because the graph looks like this. And for other functions, you can draw it out to figure out the domain. And we'll look at specific examples later, so things will be more clearer. But the domain is x has to be bigger than 0. The graph looks like this. X can never exactly be 0 if you look at the diagram here. And your range is that f of x can be negative infinity to infinity. So f of x can be any real value. But your domain has to be strictly bigger than 0. All right. And that is about all the important functions you need to know. And we'll do some calculations. And as we do calculations, we'll sort of slowly discuss more functions that might be important and ways to think about these questions and when how to solve these questions when we are asked. All right, so let's do some questions related to what we've been discussing. So basically, the first question is, which of these graphs represent functions? So we're going to use the vertical line test. And if the graph represents a function, state whether it's a one-to-one function or a many-to-one function. So we're going to use the vertical line test and the horizontal line test. All right, so the easiest way to think of this question is to visualize the graph, right? So 2x minus 3, the graph looks something like this, right? Positive gradient, so it goes, the shape looks like this, and it intersects the y-axis at -3, mx plus c structure. All right, so at any given point, if you draw a vertical line, it's only going to intersect the graph once, right? So that means it is a function. And if you draw a horizontal line, it's also only going to intersect once. So how can we tell? So if it's a many-to-one function, right? If you draw a horizontal line, it's going to intersect the curve twice. What does this mean? Well, that means that, hey, if it's intersecting twice, if you draw a horizontal line and it's intersecting twice, that means that the same output can be produced by two different inputs. So if you draw a horizontal line, it only touches the curve once. That means it's one-to-one. There's only one input that's going to produce that output. If you draw a horizontal line and it cuts the graph at multiple points, that means that it's many-to-one. Many points can map to that particular output. All right, so this graph passes the vertical line test. That means it's a function. And if you draw a horizontal line, it only intersects one at any given point. So that means it's one-to-one. All right. Sorry, I keep moving everything. Okay. So y squared minus 3. So if you draw the graph of y is equal to x squared, it looks something like this, right? And minus 3 means you just shift the whole graph 3 units down. So your graph looks something like this, as illustrated by the blue curve. So I know it looks bigger, but it's just shifting that y is equal to x squared 3 units down. Sorry about that. So if you have x is equal to 0, if you have x is equal to 0, and it's going to map to -3 here. And then so on. So every point gets shifted 3 units down. So the curve of y is equal to x squared gets shifted 3 units down. So if you draw a vertical line, it's going to pass the vertical line test. That means it is a function. Whenever you draw a vertical line, it's going to cut the graph or cut the curve at only one point. However, if you draw a horizontal line, it cuts the curve at 2 different points. That means this is a many-to-one function. So a is a function, which is one-to-one, and b is a function, which is many-to-one. All right. So we're done with 2. So a is a one-to-one function, b is a many-to-one function. All right. And let me just turn on my laptop as well. Okay, C. So the graph of C, so I remember I already showed you what the graph of y is equal to x cubed looks like. It looks like something like this. So if you multiply by 2 in front, that just stretches the graph. It makes it like this. And then -1 means to shift the graph 1 unit down. So your graph looks something like this, as drawn by the orange curve. So if you draw a vertical line, this graph is going to pass the vertical line test. So that means C is a function. And if you draw a horizontal line, that means it's also going to pass the horizontal line test. It only intersects the curve at only one point, right? Every horizontal line that you can draw will only intersect the curve at one point. So this is what we call a one-to-one function. And D. D is also going to be a one-to-one function. So 2 to the power x looks something like this. That is a to the power x for a greater than 1, right? So this is the graph. If you draw a vertical line, it's only going to intersect the curve at one point. If you draw a horizontal line, it's only going to intersect the curve at one point, right? Wherever the curve is drawn, if you draw a horizontal line, it only intersects the curve at one point. So D is also a one-to-one function. All right. E, the graph of E looks something like this. So if you want to graph 1 over x, the graph looks something like this. And multiplying by 10 does not, the shape stays the same, it just stretches the graph. So 1 over x looks something like this, and 10 over x is just this multiplied by 10, right? It just stretches the graph on the axes. It doesn't change how the graph looks like. So x is equal to 0 is not in the domain of this function. It's not defined when x is equal to 0. Sorry about that. So the function is not defined, and you are actually given a restriction. They want to only consider x bigger than 0. So we actually don't need negative value. We don't need to show the graph for negative values of x. All right. So this is a one-to-one function, obviously, right? When you draw a vertical line, it passes the vertical line test, because every vertical line you can draw with respect to the such that it touches the curve will only intersect the curve once. So it's a function. And if you draw a horizontal line, it's also only going to intersect the curve at one given point. So this is also a one-to-one function. So we are done with E. And let's look at, let me erase. So we have discussed A through E. So let me just erase. So A was a one-to-one, B was many-to-one, C was one-to-one, D was one-to-one, E was one-to-one, right? So now F says y is equal to 3x squared plus 4, and we have a restriction. So the graph of y is equal to x squared looks something like this, and 3x squared means it's just stretched towards the y-axis. It's closer to the y-axis, so something like this. And plus 4 means it's shifted 4 units up. So our final graph is going to be something that looks like the green curve. But remember, we are asked to plot only for x bigger than or equal to 0. So we don't need the left side branch of this curve. So we only need this part, x0 or bigger. So something like this. So now, does this pass the vertical line test? Does this green curve pass the vertical line test? Yes. So it's a function. And does it pass the horizontal line test? Also yes. Because every horizontal line is only going to intersect this curve once, right? So f is also a one-to-one function because of the restriction. Now, if there was no restriction, if you were considering both branches, left-hand side and right-hand side, if this restriction was not there, then it would have been a many-to-one function. All right. Y squared is equal to 4x. So y squared is equal to 4x. Let's try to visualize the graph, right? So y can only be positive because it's y squared, right? Output values are only going to be on the positive side. So 4x. So on the positive side, looks something like this. Whenever you put in any positive value of x you put in, it's going to look, the graph of y is equal to 4x looks something like this, right? And then it's also going to go down. So let's think about why this is the way. I cannot put a negative value of x here. If I put in a negative value of x, that means y squared is going to be negative something, right? And basically, if you have something squared, you cannot get a negative value. So I cannot put a negative value for negative values of x. So there's no curve on my second and third quadrants. So I can only put in positive values of x, right? And now let's consider a point like x is equal to 1. If x is equal to 1, y squared is equal to 4. So y can be plus 2 or y can be minus 2. Minus 2 squared is 4, plus 2 squared is 4. So you're going to get two values of y. So if x is 1, then y is 2, y is minus 2. So you're going to get 2 values of y for every x. So this is not a function. So h is not a function. All right. Sorry about that. Okay, h is not a function. All right. And square root of x for x greater than or equal to 0, we have discussed what the curve looks like. This is going to be a one-to-one function. So it looks something like this, passes the vertical line test, so it's a function, and it also will pass the horizontal line test. So g is a one-to-one function. One-to-one function. All right, so we are done with question 1. All right, so continuing with question 2, we are asked to represent on a graph the function. So this is called a piecewise function. So for different values of x, it's defined differently. So we have 9 minus x squared for x within this domain, and we have 2x plus 1 for x within this restriction. So one way to do it is just to plug in values. That's one way to do it. But see, let's plot the edge cases first. So if my x is negative 3, I put negative 3 into this equation, right? Negative 3 squared gives me 9. 9 minus 9 gives me 0. So if I go to my graph here, at negative 3, I have 0. Now, another point I can put within this restriction, right, is I can put 0. 0 is between negative 3 and 2. So if I put 0 here, I get positive 9. So if I put 0, I get 9. And now let's think about the nature of this graph. See, I can write this equation as y is equal to minus x squared plus 9. So if you remember, if your a is negative for a quadratic function, x squared has this shape graph. If you have negative x squared, it's this shaped. And this shape is translated 9 units up. So that is what we want to remember. So you're going to have that shape curve, right? So basically, if this, your vertex, this is usually at 0, 0, if it's negative x squared. So this point is shifted 9 units up. So remembering that, and you can also plot other points. Basically, you can plot negative 1, or you can plot negative 2. If you plot negative 2, you get 9 minus 4, which is 5. And you plot negative 1. So 9 minus 1 is going to give you 8. So something like this. And you can connect the points. So you can connect the points. Your graph looks something like this. So you don't really have to plot the middle points if you just want the shape very roughly, but it helps to plot them. Now let's continue, right? So I can plot again. I can continue with this shape of the curve until x is equal to 2. So usually you just want to draw your coordinate axes, plot some points, and then figure out the shape. But there is also a way to do the rough sketching just by imagining the shape of the graph within the restricted domain. So if my x is 1, then it's going to be 8 again. If my x is 2, it's going to be 5 again. I'm so sorry about that. Wait. Okay. 1, and if my x is 2, it's 5 again. So up until this point, I have my graph. Sorry about that. I don't know why it keeps vanishing. All right. So now for after x is equal to 2, I have this plot, 2x plus 1. So you plot 2 here, I get 5. I plot 4 here. 4, 2, so 8 plus 1 is 9. So when x is equal to 4, I have 9 again. And remember, 2x plus 4, 2x plus 1 is a straight line. So your graph is going to look something like this. So that is your graph. So state the nature of the function. And so if you draw a horizontal line here, right, you see that it intersects at 3 or 2 points. 3 points usually, right? So of course, if you draw the horizontal line at lower points, then you would think that it's 1-to-1. But you have to consider the whole curve. And at the upper points, you see that if you draw a horizontal line, it intersects the curve at 3 points. So that means this is going to be a many-to-one function. All right. So we are done with question 2. Let's go to question 3. Represent on a graph the relation this relation. Okay, so x squared. So y is equal to x squared has a graph that looks like this, and x squared plus 1 has a graph that looks like this. So it's concave up. It opens upwards, right? So from 0 to positive 2. So let's just plot. If x is equal to 0, y is equal to 1. X is 0, y is 1. And then x is 1, y is 2. X is 2, y is, I believe, 5, right? Because 2 squared is going to be 4 plus 1 is 5. And now, let's continue plotting in values. If x is equal to 2, you have... If x is equal to 2, you put it here. 4 minus 3 gives me 1. And then, this is going to be a straight line, right? With the slope 2 and y-intercept negative 3. So, just continue drawing with the slope of 2. Up until x is equal to 4. Alright. So now that I have the points, up until this point, the graph was basically a concave up quadratic function. And then, beyond, after x is equal to 2, you have a linear function. So it looks something like this. And it says, explain why this relation is not a function. So to explain that, we want to look at this point here. If x is equal to 2, then the output values are 5 and 1. So each input does not have a unique output. So one input can produce multiple outputs. So if you put in x is equal to 2, it can produce 5 and it can produce 1. So therefore, it is not a function. All right. State the domain and range for the function represented by the two graphs. All right. So for the domain, you just want to check what values of x can you put into the function. So you can put in starting from negative 1 up until 5, right? So your domain is going to be x is an element of negative 1 up until positive 5. And if I put a square bracket, that means that the elements in the edge are included. So negative 1 is included and 5 is included. Or you can write x is bigger than or equal to negative 1 is less than or equal to positive 5. And what is your range? So this function is continuous, right? It moves continuously. And I don't think it's necessary to discuss the definition of continuity. But for now, you can just imagine it to be sort of, you can ask yourself, can I draw this graph without lifting up my pen? And you can, right? You can trace it without having to lift up your pen. So that means it's going to be continuous. That's not the formal definition. That's just a way that is acceptable to understand it now. All right. So now your output values, right? Your f of x values are ranging from, the lowest it goes is negative 8. So it can be negative 8, and the highest it goes is until 8. So that is your range of output values. It goes from negative 8 to positive 8. And your domain is negative 1 to 5. And your range and domain, f of x and f of x, are real numbers, right? They're elements of real numbers. You don't really have to specify this all the time, but it's useful to specify. So your domain is that x can be from negative 1 to 5, and your range is negative 8 to positive 8 inclusive. All right, let's do the same here. Your domain is x is a real number, and it starts from negative 3. The graph is continuous. It goes up until positive 2. And your output is also a real number. It goes as low as negative 7 and as high as 20. So negative 7, f of x, 20. So that is your domain and range. Basically, your set of outputs. You are outputting values starting from negative 7 to 20, right? Every x between negative 7 and 20, as you can see when you trace the graph, is going to be included. And every x value from negative 3 to positive 2 is included as you trace the graph. So that is how you figure out the domain and the range. All right. And that is it for question 4. Let's move on. Question 5. Find the range of each of the following functions. So 5a, let me write the function down. F of x is equal to x plus 4 for x bigger than 8. So let's try to visualize the curve. So if the graph of x plus 4, right, looks something like this. So your y-intercept is positive 4. And you want to consider it after x is equal to 8. So if x is 8, your output value is going to be 12. So you only want to consider this part, the orange part of the straight line. You don't want to consider even x cannot be 8. It's always bigger, right? So your output, f of x is going to be real. F of x is going to be bigger than 12. If it's 8, it's exactly 12. But because it's not going to be 8, it always has to be bigger than 12. So that is your range for A. All right. For B, so this is, again, you want to visualize the function, right? It has a positive slope and it intersects here. It looks something like this. And because from the shape of the graph, you can see that this is a one-to-one function and this is an increasing function, right? As x increases, the output is increasing. So therefore, you can just plug in the values for the edge cases. You can't do it for all the functions, but if it's an increasing function that is one-to-one in this case, then your f of the range is just going to be f of negative 3, f of x, and then f of 2. So this works for this case. Because negative 3, it's going to be here, and then it goes up until whatever the value is when it's positive 2. So if I substitute negative 3 here, I get negative 13, I believe, f of x, and if I substitute 2 here, I get negative 3. So that is my solution for B. For C, it's the same thing, but this time, it's going to look a bit different. Why? Because the graph is decreasing, right? So the y-intercept is positive 7, and I have a negative slope. So the graph looks something like this. So if I put in negative 1, my output is going to be higher. If I put in positive 4, which is the negative 1 is here, positive 4 is here, my output is going to be lower. So the range is going to be this set of values represented by the green line. So my range is just going to be from f of positive 4, because that's lower, right? And then f of x, f of negative 1. So what is f of 4? If I put in 4 here, it's negative 1, bigger than or equal to f of x, less than or equal to, if it's negative 1, then I believe it's 9. So that is your range for C. Let's go to D. So this is another notation for a function. Basically, you have a function f, and it maps the input x to 2x squared. That is what this is saying. So you have a function f, it's mapping your input variable x to 2x squared. So let's visualize the graph of 2x squared from 1 to 4. So the graph of 2x squared looks something like this, and we just want to consider it from x is equal to 1 up until x is equal to 4. All right. So your output values is going to be the one shaded in dark values, the dark blue line. So it's going to be, your range is going to be f of 1 within this, right? You can sort of figure it out from the graph. So your set of output values is going to be represented by this inequality. So 2, starting from 2 up until 32. That is your range of output. All right. E says f of x 2 to the power x. The graph looks something like this, right? So it's an increasing function again. So you can just plug in the values to get the range. So you have f of negative 5, f of x, f of 2. So you want to visualize the graph. And because it's increasing, I don't really have to worry about anything. I can just plug in negative 5. That's going to give me a lower value. I can plug in 2. That's going to give me a higher value. And my function, the output values, is going to be within this range, right? As represented by the green line. So f of negative 5 is 1 over 32. 2 to the power negative 5 is 1 over 32. And you have f of x and up until 4. 2 to the power 2 is just 4. So let me turn on my laptop so we can check. Sorry, it's negative 5 up until 4. I'm so sorry. This has to be 4. So 2 to the power of 4 is 16. So 1 over 32 till 16. We are done with E. And finally, F. So you have f of x is 12 over x, right? And 12 over x has a graph. So we are only considering the positive arm of this graph. So something like this. So this is 12 over x. And this comes from the graph of 1 over x that we previously looked at. So if you have to draw 1 over x, then it looks like this. And you also have a negative branch here, but we're only considering positive x values. So this is enough. So you put in f of x is equal to 1, you get a high output. You put x is equal to 8, you get a low output. So and this is sort of a continuous function here, right? So you don't have to pick up your pen. So your output range is going to be within this green values. So your output, f of x, is going to be bigger than or equal to your output when x is equal to 8, and it's going to be smaller than or equal to the output when x is equal to 1. So 12 by 8, which is 3 by 2, I believe. 3 by 2, f of x, and 12. So that is going to be your range. All right, so we are done with question 5. So this is your range. This is your range. All right, so we are done with question 5. Question 6 is the same question. Find the range for each of these functions. So you want to draw your functions out. That is the best way to do it. F of x squared, if you only had x squared, your graph looks something like this. You have x squared minus 2. It shifts 2 units down. So your graph looks something like this. So your output is going to be all real numbers that are bigger than or equal. This is your minimum point. You cannot have outputs less than this, right? So your minimum point occurs when x is equal to 0. So this is going to be negative 2. So your output, which is f of x, is always bigger than or equal to negative 2. F of x is always bigger than or equal to negative 2. So that is the range for A. B. So now you do the same thing. You draw your curve, x squared plus 3. You shift it 3 units up. So your output, now you are given a restriction actually. So this one had no restriction. This one has a restriction. So we only want to consider this from negative 2. So if you put negative 2 here, you get positive 7. And if you put x is equal to 5, right, you get 25 plus 3 is 28. And your graph looks something like this. So I know you might be tempted to say, well, the range is from 7 to 28. Remember, it goes lower. Your range actually is from 3 to 28. Because if you substitute 0 here, you get 3. So it can take any value. The output can take any value within the dark green area. The orange area here just is a repetition of some values that is already included here. So your f of x is bigger than or equal to 3 and then less than or equal to 28. So that is your answer for B. All right. For C, we're going to draw the graph again. I'm so sorry. Let me erase. So we're done with 6A and 6B. So let me just erase so that we avoid confusion. And all right, so we're done with question 6C. So 3 minus 2x squared. So the graph of minus x squared is concave down. Looks something like this, right? And then you're adding 3. This is plus 3. Minus 2x squared looks something like this. You're adding 3. So it shifts upwards. So your graph looks something like this. This is positive 3 here, right? For x less than or equal to 2. So if you substitute 2 into this equation, 2 squared is 4. 4 2 is 8. 3 minus 8. So if x is equal to 2, so let's just say I have 2 here, then I get 3 minus 8 is negative 5. So I get, if x is equal to 2, then I get something like negative 5 here. So, and the condition that x is less than or equal to 2. So I have range of values for like this, right? So I don't need to consider anything bigger. So my range of values, so if you think my range is just going to be in this light blue area. That is going to be my range, because this light blue area already covers the y points that I have drawn on the right hand side with the red line, right? So my function f of x is going to take values that is less than or equal to positive 3. So that is going to be my range for C. And for D, I have something similar. So the graph is going to look something like this if I draw it in its totality. If x is equal to 0, then y is equal to 7 here. So now that I know the shape of the graph very roughly, let me just substitute the points. If it's -1, I put -1 here, I get 4. Let's say 4 is here. If I put positive 2, then I have 7 minus 12, which is -5. So putting positive 2 gives me -5. Yeah, I think. I believe it does. Okay. So my function, I only need to consider this part of the graph, the one that I'm showing in red. So what are my possible output values? Well, f of x is always less than or equal to 7, right? 7 is the maximum it can take, and -5 is the minimum that it can take. So it's going to be bigger than or equal to -5 here, and it's going to be less than or equal to positive 7. All right, so now we are done with question 6. Question 7. Find the range of each of these functions. This is an interesting one because it's not that easy to draw the graph. So let's just draw the graph of y is equal to x squared. Look, that looks something like this. X minus 2 squared basically means if I have x minus something, right? So minus 2 means I want to shift this graph 2 units to the right. Minus, if it's plus 2, then it's 2 units to the left. Minus 2 means 2 units to the right. So my graph, so this point shifts 2 units here. This is 2. And now it looks something like this. But that's not all. I need to shift 5 units up as well. So now I need to shift my new graph, the pink graph, 5 units up. So it looks something like this. So this point is 2, 5, right? So when I shifted it right, it shifted from 0 to 2. Now it shifted 5 units up. So my vertex is at 2, 5. And 4x is bigger than or equal to 2. So I just need to consider the red arm. And you can observe that the range is just f of x is bigger than or equal to 5. So that is your answer to 7a. 7b. So 2x just stretches my graph. I don't really need to worry about that. So 2x squared would also look something like this. Minus 1 basically means I need to shift it 1 unit to the right. Something like this. And then minus 7 means 7 units down. So my graph looks something like this, as represented by the green curve. And it says for x bigger than or equal to 1/2. So let's just substitute 1/2 here. And I believe that gives us -7 at x is equal to 1/2 and here. So your range output, so if you substitute half, you're going to get the red arm of the branch. So x is 1/2 is when y is equal to -7. That is the coordinate of my vertex, right? And basically, if it's bigger, then it starts taking these values. So you can see that your output values are bigger than or equal to -7. That is going to be your answer to B. All right, so let's erase this. So we can draw for C. So we have negative, right? So negative x squared, the graph looks something like this. And minus 5 means shift this graph 5 units to the right. So it looks something like the one I have drawn in purple. And I have plus 8. That means shift it 8 units up. So my graph looks something like this. And I am given from 4 to 10, right? So if I substitute 4, so let's get the equation of my vertex. My vertex is going to be at 5, 8. 5, 8 is where my vertex is, because I shifted 5 units to the right and 8 units up. So my vertex point from 0, 0 shifts 5 to the right and 8 units up. So this is something that we have been discussing when we also discussed from graph transformations when we did chapter 3. So negative x squared looks something like this. This tells me I need to shift it to 5 units to the right. This tells me I need to shift it 8 units up. And we will discuss this in more detail in a later chapter. So if I substitute x is equal to 4, here I get 4 minus 5 is negative 1 squared is 1, 8 minus 1 is 7. So I have 7 when x is equal to 4. And 5, I have my vertex, and then I need to substitute 10. 10 minus 5 is 5, 5 squared is 25. 8 minus 25 is going to be, I believe, negative 16. Is it? 8 minus 25. Negative 17. All right. Negative 17. So your output values are going to be within this blue line range, right? So that means that f of x, so the maximum value in this range is less than or equal to positive 8, and it's bigger than or equal to negative 17. So that is your solution for C. And for D, we have this. All right. So minus x squared would be like this, and then I need minus 3x squared would also be like this. It's just stretched, and then I need to shift it 7 units up. So I have a graph that looks like this. Now let me just substitute my points. If I substitute negative 1 here, I get 7 minus 3, which is 4. And then if I substitute positive 2 here, then I believe we've done this question, right? You get 7 minus 12. 7 minus 12 is negative 5. Yeah, I remember doing this. Okay, I made a mistake. We're doing 6D again. I'm so sorry about that. We're supposed to be doing 7D. All right. So now let's remember the square root function. Your square root function looks something like this, right? And this just tells me to shift my square root function 4 units to the right. X minus 4 means shifted 4 units to the right. So my graph looks something like this. This is 4, and I need to shift it 1 unit up. So now I shifted 1 unit up. So this point is going to be 4, 1, right? Shifted 4 units to the right, 1 unit up. This point is now shifted to this point, to 4, 1, from 0, 0. And basically, it's taking on every value. It is going to cover every real number that is bigger than or equal to 1. So therefore, your range is bigger than or equal to 1. And that is it for question 7. Question 8. Express each function in the form of this. So basically, complete the square and hence state the range of each function. All right. So I have x squared plus 6x minus 11. X squared plus 6x minus 11, f of x. So I can write this as x plus 3 squared, which is x squared. So you can use completing the square method. Now I'm going to do it a bit quicker because we've discussed this at length before. So x plus 3 squared gives me x squared. 3 times x is 3x times 2 is 6x plus 9. But I don't want 9. I want minus 11. So I need to subtract 20, I believe, right? 9 minus 20 will give me minus 11. So if you complete the square, you get this expression. So now, let's see. We can visualize the graph, right? If I had x squared, then it would look something like this. But I have x plus 3 squared. So I need to, if I had minus, I was shifting to the right. If I have plus 3, I'm going to shift it 3 units to the left. So something like this, and then 20 units down. So I shift my new green curve 20 units down. So it looks something like this. And my vertex is at negative 3, negative 20. All right. So now I need to find the range of each function. So my range is just going to be from the minimum point to every other output, so all possible output. So therefore, my f of x is bigger than or equal to negative 20. That is going to be my range for 8a. And for 8b, we're going to do something similar. So for b, I have f of x is equal to 3x squared minus 10x plus 2. So you factor out your 3, you get x squared minus 10 over 3x plus 2 over 3. And now let's try to complete the square. I have 3x minus 5 over 3 squared. So that gives me x squared minus 10 over 3x. And now I have, if I square 5 over 3, I get 25 over 9. So I'm going to do it a bit quickly. But let me just show you the idea. I want to take half of my b term and then put it inside the term that I'm squaring, right? So half of 10 over 3 is 5 over 3. So I put x, I copy the sign here. So x minus 5 over 3 squared. And if you square this, if you expand it, you get x squared minus 10 over 3 plus 25 over 9. But I don't want 25 over 9. I want 2 over 3. And 2 over 3 is just 6 over 9. Right? So I need to subtract something from 25 over 9. I need to subtract 19, I believe, right? If I subtract 19 over 9, then I get 6 over 9. So I need to subtract 19 over 9. All right. And now I can multiply by 3 inside. So I get 3x minus 5 over 3 squared minus 19 over 3. So if I multiply by 3 here, you get, because 9 is 3 times 3, right? So when you multiply inside, the 3 is going to cancel out, and I'm left with 19 over 3. And then I also need to multiply 3 here. So now I can visualize the graph. So 3 is positive, so it's going to be concave up, right? So if it's x squared, then it looks something like this, but it's x minus 5 over 3. So I need to shift it 5 over 3 units to the right. So this is 5 over 3, and I need to shift it 19 over 3 units down. So something like this. So this is positive 5 over 3, comma, negative 19 over 3. So therefore, your range is going to be f of x is bigger than or equal to negative 19 over 3 is bigger than or equal to, if you now write this as a mixed fraction, it's negative 6 1 over 3. All right, so that is your solution to question 8. Question 9. Hence, express each function in the form of this. Basically, is asking you to do the same thing. So 9a gives you 7 minus 8x minus x squared for all x is real numbers. So we don't really care about that. So f of x, let me write as 7 minus 8x minus x squared. So let me factor out a negative sign first. 7 minus 7, right? So I will get x squared plus 8x minus 7. If I factor out a negative sign here, I get this expression. Now, I can write this as x plus 4 squared. So I get x squared plus 8x plus 16. And then I need to subtract something to get to negative 7. So if I have plus 16, I need to subtract 23, I believe. 16 minus 23 gives me negative 7. So I have, now if I distribute the negative sign inside again, I get 23 minus x plus 4 squared. Now I can visualize the graph. I have negative x squared, right? So negative x squared looks something like this, concave down. And then I need to shift it 4 units to the left because it's plus 4. 4 units to the left, and then it's 23 units up. So my final graph looks something like this. And my vertex point is at negative 4, comma 23. So your f of x is going to be less than or equal to positive 23, if you think about the range. So your range is going to be always lower, so your output values are not going to exceed 23, less than or equal to 23. All right. And for part B, it's the same idea. You factor out a negative 1 first, and I get 3x squared plus 6x minus 2. And then you just complete the square. So I factor out a 3 as well. So I get x squared plus 2x minus 2 over 3. Now I can complete the square. I have x plus 1 squared. I have x squared plus 2x plus 1. And then I need to subtract 5 over 3, right? Because 1 is 3 over 3. And if I take away minus 5 over 3, then that gives me negative 2 over 3. All right. And then I can multiply by 3 inside again. So I have negative 3x plus 1 squared plus 5. If I multiply by 3 inside again. All right. So now I can visualize the graph here. Negative 3 is just a stretch, but negative x squared has a graph of something like this. And then I have x plus 1, so I'm shifting it 1 unit to the left. And then I'm shifting it 5 units up. All right. So I have negative 1 comma 5 here. So f of x, so your output values, as shown here, is always going to be less than or equal to 5. So we are done with 9b. So let's go to question 10. Represent on a graph the function, this one. So let me just pull out my coordinate axis here. So 3 minus x squared minus x, I'm so sorry. Minus x squared has a graph like this, and then I'm shifting it 3 units up. So the graph looks something like this. For the range 0 to 2. So 0, and then when it's 2, it's negative 1. All right, so we know how to plot it. So if I have 0, then I am at positive 3, right? So if it's, and then when it's 2, I am at negative 1, and I know roughly the shape looks like this. But let's just plot the graph when x is equal to 1 as well. So if x is equal to 1, 3 minus 1 gives me 2. So this point is included. And I have 3x minus 7. So when x is equal to 2, right, I get negative 1. And then when x is equal to 4, 12 minus 7, it goes up until 5. Goes up until 5. So my graph is just a straight line that looks something like this, or with a slope of 3. So that is going to be your function. And find the range of the function. Well, the lowest that my function outputs to is negative 1, and the highest that my function outputs to is positive 5. Any number from in this part is already included, is going to be included in the orange part, right? So my range is going to be from negative 1 f of x to positive 5. All right. So that is, so if you pick a better scale for your graph, then your graph is going to look much better. But that is going to be your range from negative 1 up until positive 5. All right. So we are done with question 10. Question 11. So the function is given as follows. Find the range of f in terms of k. So we have f of x is x squared plus 6x plus k, right? So now I can complete the square. Well, I can write this as x plus 3 squared, right? So x plus 3 squared is basically, I have x squared plus 6x plus 9. So I need to take away 9 and I need to add an x. And if you expand this out, you're going to get this equation again. So I have plus 9 here, which I don't need. So I subtract 9 and then I need to add a k. All right. I have this expression here. So now I can visualize the curve. If you visualize the curve, then you're going to get something like this. You have x plus 3. So x squared is usually like this. You are shifting it 3 units to the left, x plus 3. And then you're shifting it by this. So you're shifting it. We don't know what minus 9 plus k is. It could be positive. It could be negative. But this is going to shift exactly by whatever minus 9 plus k is, right? So if it's negative, you're going to shift down. If it's positive, it's going to shift by minus 9 plus k units. So this is going to, this vertex point is going to move to minus 9 plus k. And it's concave up, right? So therefore, your f of x is always going to be bigger than or equal to minus 9 plus k. So that is your range. So f of x is always bigger than or equal to k minus 9. Minus 9 plus k or k minus 9 is the same thing. So that is your solution. Question 12. The function 5 minus ax minus 2x squared. 5 minus ax minus 2x squared. Where a is a constant is defined for it. Find the range of g in terms of a. Alright, so we need to find the range in terms of a. So let's subtract out a negative sign first. If I do so, I have 2x squared plus ax minus 5. And then I can factor out a 2. When I do so, I have x squared plus a over 2x minus 5 over 2. Now we will complete the square. if I complete the square, I will get x plus a over 4 squared. And if you use the binomial formula, or if you try to expand this out, you will see that my first two terms are gonna match. Now, if I square a over 4, I get a squared over 16. So I don't need a squared over 16. I need to take that away, a squared over 16. So now I have x squared plus a over 2x. And I took away a squared over 16, but I still need minus 5 over 2. So I still need minus 5 over 2. All right. And now I can multiply inside by 2 again. I have minus 2x plus a over 4 squared minus a squared over 8. Sorry, plus, right? Because you multiply by minus 2 on the inside. So you get plus a squared over 8 plus 5. And it's the same idea. So you have minus x something squared. So the graph would be looking like this. You shift it by a over 4 units. So that's only going to shift it horizontally. And then you shift it by a squared. So you're going to shift it up, right? This is going to be a positive expression. So you shift it up by some units, by this unit. So then you can see that your range for this function is going to be f of x is always going to be less than or equal to a squared over 8 plus 5. That is your answer. So that is why, like, knowing quadratic equations, knowing how to draw the graphs, knowing how to shift the graphs is very, very important here. A squared over 8 by plus 5. All right, so we are done with question 12. Question 13.